One of the things I hope you got from the lab is that things are made of smaller particles. So, all the substances that you are familiar with, including your own body, is made up of various components. And those components are then made up of other components. And the smallest component. Now this is key. It's subtle. It's not the smallest component of all matter, but it is the smallest component that retains. That means keeps, right? That retains the properties of the material we call the element. The word element has a long history, and there was a time when people thought, including some of the academic fathers of science, thought that all things were made of fire or air or water or earth. And the Chinese even have this word called qi. They add another one of these basic elements that they thought made up all things. Today we know that these elements are made of these things we call atoms. And there was an ancient Greek who thought of this concept that all things were made of these tiniest indivisible particles. And really that's the idea, is that atoms are indivisible, right? In other words, you can't break them up in chemical reactions. Now, of course, an atomic bomb is the breaking of an atom, and we have whole super colliders to smash them up. But when it comes to chemistry, atoms are indivisible. They're the basic unit. And the types of atoms we call elements. So elements are different types of atoms. And it's these elements and atoms that come together to form molecules. And those are the things that you looked at. Those are the things you mixed together in different solutions that came together and made a solution. And in this case, atoms come together to form water and whatever else is mixed in this water. Because the rain that falls from the sky often is not just rain. There's other molecules in there with it. Sulfuric acid, possibly. Small amounts, but still. There's all kinds of things that could come into a cloud from a volcano that erupted halfway across a continent. So when rain falls, it's not necessarily just rain. Probably the most common component is some carbonic acid, which is when CO2 mixes with water, it forms carbonic acid. That's one of the types of acids you have in your drinks, your soft drinks. But in any case, the point is it's not pure water that's falling from the clouds onto the land. And it's one of the sources of pollution on the soil and in our water supply. But in any case, let's move on and try to think about and connect our experience in the lab with what we have to learn about chemical reactions. And we're only learning the very basics of it. Next year, you'll have a whole class on chemistry. But what we do learn, you must know, or you will be at a disadvantage throughout the year. So the types of chemical reactions we talked about is these four here, and actually we talked about five because we added a combustion reaction. And there's all kinds of different ways of organizing these and naming these. These are not the only types, but these are the basic types that most people agree are pretty stable. We added this fifth one called combustion, and that was important, as you saw when we were trying to combine hydrogen and oxygen. So in a combustion reaction, you have any kind of, you have an A, and you're combining it with oxygen gas, and you're going to release a lot of energy, and that could be a fire or that could be an explosion, and you're going to make CO2, and you're going to make water. Now, some people would call that hydrogen reaction combustion. Technically, it's not, because you're not forming CO2. It's not that concept that we talked about, that was that type of molecule that we talked about, that we said was a hydrocarbon, right? And remember, that's just a bunch of carbons connected and hydrogens sticking to these as well. Now, there are rules to this, and the number of bonds that an atom can make, and you're going to learn them. And you're only going to learn probably 5 or 6 atoms and how they act. And the reason it's important that you cover these 5 or 6 atoms, and of course specifically hydrocarbons are going to be one of them, is because those are the elements, those are the 6 or 7 elements that are going to be the basis of all the chemistry we're going to be talking about all year long. So hydrocarbons are, again, a bunch of carbons bonded together. We're going to talk today a little bit about what these bonds mean, and we're going to talk a lot more of it about that next week. You're going to need to really buckle down and get these definitions and these ideas in your head. And if you find it difficult to get in your head, you need to come to the tutor. You need to look up videos, whatever it is you need to do. So this would be an example of a hydrocarbon, and there's all kinds of names that you need to, in some point in your education, you'll have to know. But for now, you just need to know that this is a hydrocarbon. Is anytime you have a carbon, a bunch of hydrogens. Sometimes there's an oxygen in there, but not much, not many. In any case, you have this synthesis reaction where you're taking one thing and you're putting it together with another thing, and you're coming up with one thing, right? So in the synthesis, you're taking more than one and you're making one. You're bonding them. There's that word bonding again. It's the same kind of thing that you see these lines. See these lines that are connecting them? They represent a bond. You really need to take a moment and think about what that means. What is a bond? What is a bond? We saw in the video, that the little animation I made, and we talked about it in class, that these things are switching, they're exchanging, they're taking over, right? Because we really focused in on single displacement reactions in the lab, and there were some double displacement as well. However, a lot of you guys weren't able to get to the double displacement reaction. There were no decomposition reactions, and I know what people were thinking. Not only did I watch the videos, and I had a lot more footage in the video than I sent you, but I also listened while you were discussing, by the questions that you were asking me as well. I think it was obvious that you were thinking, when you looked inside that reaction vessel or beaker or vial or whatever it was that you were using to react these two substances, this A and this B. Now, I need you to understand, A and B here are not atoms. They do not represent atoms in this case. These are variables. There is no element A by itself. And B, there is an element B, but this is not it. This is not what these represent. These represent variables. So some substance A, which could be anything, is being mixed with substance B, and you're getting a new thing. Okay, the key is you're getting a new thing. In all of these, you're getting new things, you see. These things have properties, their color, their pH, right? Their density, their, any number, the metallic nature of them, how shiny they are, how blue are they, how transparent are they soluble in water? All these things changed, didn't they? Think about it. That's the key here, is the word change. So the idea here is that something changed, something big, something fundamental. Yes, they were small changes. I'm not going to put you in danger and give you TNT, right? But they were small changes, but still changes. And it's the same fundamental kind of changes that happen when you do explode TNT or C4 or any of the other things that you see in your video games. These things called changes, these chemical reactions, they're fundamental changes in what these things are, right? So they started as one thing. They had certain qualities, and you described those qualities, I hope, in your lab reports. You described, they were metallic, or they were solid, or they were in aqueous solution, which means they're in solution. We'll talk about that next week as well. In fact, our lab this week is about solutions. So when we look at these ideas that when we mix these two things, 1 and 2, and we put them in together, right? In some cases they were solid like the copper metal, or in some cases they were two liquids, right? And the liquids had little particles in them. We'll talk a little bit about what those were today. And what you saw was when we mixed them together, there was these changes, any one of these 5 changes. Now, we know today from what I told you that there were no decomposition reactions. We didn't go from 2 things and make 1. Now, I think I know why some people thought that. They looked at this thing, this copper strip, right, the Cu copper strip, and they saw it kind of, things started to appear, right? And it was a color change. It was a silvery change, but it looked like when you looked at it that the copper was dissolving, was breaking apart, right? Breaking apart. And right away you thought, breaking apart, it's decomposition. Well, I can understand that. In this case, it was wrong. Okay, it was not breaking apart. And if you thought about it, if you had done your pre-reading and really thought about it, and I just read it, right? Because I know a lot of people read it. I heard you, and you guys had at least familiarized yourself with the procedures, which is the most important thing when it comes to a lab. But the second most important thing is trying to understand the concepts. What exactly is a single displacement reaction? What can I expect to see in reaction 1, in reaction 2, reaction 3, 4, 5, and 6? And what you should have known by reading is that you were dealing with single replacement reactions and double displacement reactions. There was really only one synthesis that you were creating, that was going on, and that's when we took hydrogen and we combined it with oxygen. So we had 2 things, hydrogen and oxygen, right? 1 thing and 2 things, and we combined them, and here's that arrow, yielding. And what did we yield? Well, hopefully you remembered water, right? So we made water. I hope you realize that. This is the only real synthesis we had going on, but there was no decomposition. Now, this particular example I explained in the video numerous times, and there were several examples. So there's really a lot of good examples in the video and in our discussion points in class, and again, discussions in the video of single replacement reactions and double replacement reactions. What you're dealing with is ions are exchanging. Now, what's interesting about single replacement reactions, and something you should make a note of if you're one of those people that like to get good grades on quizzes and tests, is that in single replacement reactions or displacement reactions, what happens is one of the substances is displaced. You'll notice that one of the key examples in this type of reaction is that you get a fundamental a displacement of a substance, of an atom or an element, or ion. And what happens is that usually, in the case of the copper and the silver, precipitates happen. Now, with double replacement reactions, atoms or sections of a molecule, because it doesn't just have to be one atom, right? Remember, and I'll just point this out, that nitrate, NO3, is actually, if you looked at that video, if not, go back and look at it again, is actually nitrogen with 3 oxygens. And that was combined with, I'm going to put a little square bracket around it because it has a negative charge, and we'll talk more about that later, with some type of ion that you see there's silver, in one case silver nitrate, right? Or it was combined with copper for copper nitrate, or it was combined with zinc for zinc nitrate. So any one of these could substitute for for combining with or attaching to this nitrate, right? So this nitrate could go with any one of these 3. And there's an actual order to them. It's called the Reactivity Series. One of these is there's one that's the most likely to bond to nitrate, and one that's least likely, and then there's one that's in between. So each one is displaced, almost like a pecking order, right? One is more likely to be found bonded to nitrogen than nitrate than the other 2. So these are types of bonds, and these are, first of all, they're types of chemical reactions. They're kinds of changes that happen, and there's a lot of questions that come. There are more questions than answers from this lab, I hope. What is a bond? How come copper kicked silver out? How come zinc kicked copper out? You see, copper is more reactive with nitrate than silver is, and zinc is more reactive with nitrate than copper is. Why is that? What is going on with these bonds? How are they exchanged? How come energy is released? How is it that you have this hydrogen combining with this oxygen, right? And all of a sudden you have this energy being released. No CO2, right? Because it really wasn't a combustion reaction, although some people would call it a combustion reaction. It was not a combustion reaction. It was a synthesis. So in this synthesis, you released all this energy, and you made water, which there's some similarities to combustion, right? You're making water, and you're releasing energy. The only difference is you're not making CO2. So you're producing this new thing, and you're releasing this energy. Where'd the energy come from? Why was the energy released? So this is really key, because you run on energy, and you run on this chemical type of energy, and there's these specific molecules we'll be talking about in about a month that are very important to how you work and whether you live or die. And it's really important that you understand, for the sake of your grade, for the sake of your graduation, because it's the end of course exam, it's important on the end of course exam, but also for the sake of you just understanding how you work. And then, of course, there's this idea that a lot of you have, according to what you've told me, that you want to be doctors and nurses and be in the medical field or in the research field. If this is true, if you want to do anything in medicine, then you need to start understanding these basic concepts of not only how things work, because this goes for gasoline in your car, as well as water vapor and rain falling from the sky, and global climate change, but also how your own body works. What is it that happens to sugar when you eat it, and how do you get it into your body, and what happens to it after it gets into your body? These are fundamental questions to a lot of us. All right, let's go on to the next slide. So here are the elements. These are all the elements that we know of. I believe there's a few more, maybe. No, this has all 115 of the elements that we know of up to now. Now, there's 115 elements known, but we really, we are in biology, as far as how your body works. These numbers, these high numbers down here, really not incredibly important to how your body works. They're rare. A lot of them are radioactive. Life really doesn't depend on these unstable elements. Life really depends truly on these first four rows of the periodic table. Of course, there are other exceptions. There are some elements down here that are important, but in smaller amounts, of course. In any case, when we're talking about the important elements of the periodic table, well, the elements you have to be thinking about are, start with hydrogen, of course, and they run all the way over to this column. All right. These are called noble gases. And noble gases are called noble because they don't react very well. They tend not to react. You know, like the nobles of ages past. They don't deal with the peons or the peasants in the rest of the periodic table. So when we look at the elements in this giant group, and really, if you really want to get down to it, you're probably talking about these guys here and these guys here as being probably the most important. And I'm kind of pushing it with bromine and silicon for life. There's some silicon. There's some organisms in sea vents at the bottom of the ocean that have a lot to do with silicon. But of course, iron is going to be important, and of course, you have some copper is important to your bodies. You know these from your vitamins that some of you take. Zinc, silver, not so much. Really, that's about it for your body, for human consumption. So if we're looking at kind of the elements of life, there they are. You know, the others will be involved in a molecule or two or in a vitamin, and they may be very important. But these are the ones that you really have to concern yourself with. You need to know these, and if you look at it, there aren't that many. And I would even say, don't even worry about bromine and silicon. Really, the ones that I would say, if you're in dire need of making things simple for yourself, then I would definitely know hydrogen. This is not a good color. So let me just do the light. You need hydrogen for sure. You need oxygen, right? Nitrogen, phosphorus, sulfur, chlorine, carbon, of course. Probably sodium and potassium, and calcium. Lithium is important, not only in batteries, but in your brain activity. Beryllium, yeah, magnesium, okay. They're important. But if you're really looking for, what are the ones I'm going to see most often? Hydrogen, sodium, potassium, somewhat calcium. Carbon, yes. So, number 1 and number 2, carbon and hydrogen. And 3, oxygen, of course, oxygen. So 1, 2, and 3, hydrogen, carbon, and oxygen. And nitrogen, of course, there's 4. And phosphorus is 5. As far as like if it's the most important, you really can't say that. Is DNA important? Then phosphorus is important. And nitrogen, of course, and oxygen is important for life. I think you all know that. And carbon is what we're all made of, as we saw in the hydrocarbons. And 2 is, of course, chlorine is going to be important as well. So this is probably a 6. But again, for me to sit there and try to tell you that chlorine is more important than sulfur, it's arbitrary at this point. But if I'm going to say 6 and 7, so if you know these 7, so that's carbon, hydrogen, oxygen, nitrogen, phosphorus. This is supposed to be a 7, unfortunately. Sorry to see. Chlorine and sulfur, if you know those elements, you're going to be in good stead with knowing the elements you're going to need for the rest of the year. Calcium, of course, as I said, a little dot will be important. Of course, there's one that's left out, and you know, if we say, I'm going to go ahead and say 8 over here. This is a big one. Iron. It's in your blood. A lot of anyone that's anemic knows that it's important. Of course, zinc and copper. You can find zinc for sure in your body. All right, so these are kind of the 8 main elements that you're going to need to get familiar with, and how they act and react are going to be very important. We're going to focus on carbon chemistry, and that's going to be incredibly important. It's probably one of the ones you're going to get to know really well, and you're going to need to know how hydrogen fits into this and how oxygen fits into this. So, you know, there's C, H, O, N, right? CHN, and then P, chnops or chomps, and sulfur. So, you know, these are really kind of your baseline, your backbone to everything, and then everything else, the rest of these 8 are going to be something you need to know. So of all these elements in the periodic table, really, we're going to focus on these 8. So what is this bonding thing we're talking about? And again, we'll have to talk a little more. We're going to focus again on carbon, and the rest of the elements pretty much do the same thing. But I'm only concerned about the elements that we need to know for our biology class. If you take a look at how elements, and by the way, if we had more time, if we didn't have an end of course exam, if we had more than 53 minutes or 57 minutes a day, I would say, okay, we can spend a little more time on some of these other elements. But when we have to sit down and focus on what we need to know, this is what we need to know. So sharing electrons is one type of bonding, and these electrons are on the outside of the atom. The center of the atom is made of these things called protons, and they're tiny particles. And we arbitrarily give them, it's not arbitrary, there's a whole lineage of experiments that you learn about in physical science. Hopefully some of you have had that class and have learned about these experiments. There's this gold foil experiment, very famous experiment, that looked at shooting particles through a gold foil, and depending on how they diffracted, how they bounced off, they were that scientist was able to tell us that atoms are made mostly of space. Now that's intense if you think about it. If you're made of atoms and atoms are made mostly of space, then you're made mostly of space. In the center of the atom, so you need to think about a stadium. A stadium is big as Gund Arena. A stadium is big as our baseball or football stadiums, okay, in Cleveland. Let's think about football. So if you had a stadium, and in the very center of that stadium, you had a baseball. So a baseball in the center of a stadium, that's the center of an. That's the difference between the center of the atom and the outer shells of the atom. So when we talk about an atom having a nucleus, the nucleus is incredibly tiny, yet most of the mass of the atom is here in the nucleus. And that mass is made of protons that have positive charges and electrons that have negative charges. Now, electrons have very little mass. Very, very little mass. So much so that when we calculate the mass of the atom, we're really just worried about protons and their Neutral cousins, neutrons. Yes, I know you've all heard of Jimmy Neutron. The neutrons have no charge, but they do have the same mass as a proton. So these two have the same mass, where the electron has very, very tiny mass. All right. So this is going to be very important, believe it or not, because you're going to have to, at some point, probably, well, let's go ahead and say it, next week, you're going to have to calculate, if I tell you the mass of an atom, and of course we're going to stick to our 9 atoms, the mass of carbon is, a certain number, then you should be able to tell me, if you know the mass of carbon, you should be able to tell me how many neutrons. Now, how would you be able to tell that? Are you able to tell it now? No, you're not. More likely than not, you're not. But this is a question you will need to be able to answer by next week. So when we're going through this, pay extra attention when we're trying to figure out what's the mass. When you have the mass, how do you figure out the number of neutrons? If I know the number of neutrons and I know the mass, can I figure out what element I have? So we'll talk more about that. But that's one of those things that you have to think about when we're talking about the structure of an atom. The reason the structure is so important is it gives us a lot of information about what's happening with a particular atom. And of course, if you understand the atom and how it works, then you understand how things combine and recombine, how things conduct electrons, the passing of electrons, and therefore chemical reactions. So you can see here the protons in the center, the electrons on the outside, and electrons can be shared. You see these two being shared here? That creates a bond, a very strong bond, much stronger than an ionic bond. This is called a covalent bond, and we'll talk about that. And there's a lot of implications. Oh my God, there's so much that depends on you understanding this idea of covalent bond versus ionic bond, okay? Another important concept as we go through and we try to explain this next week, that you focus on this idea. What is the difference between a molecule? This is a molecule. This is the stuff that we mixed into liquids, into water, and mixed together in a beaker, and ionic bonds and ions floating in the solution. Okay, so that's it. That's the kind of little intro I wanted to make sure I sent you. I know you're not going to watch it tonight. It's late. I just got to it. So hopefully by tomorrow maybe I'll be able to show it in class. It depends how things run and how well we're able to get through the debrief on the lab. The key is to all this, as you can tell, where are we going? What do we have to focus on? What is our goal? Our goal is to understand what it is, what an atom is, what are its parts, how do I find mass, what the elements are that make up life, what kinds of bonds do they make, and then we'll talk more about their chemistry in the weeks to come. All right, well, you have a great evening. Well, if you watch this tonight, if not, you have a great day tomorrow, and hopefully we're all on time and chipper and ready to do some hard work. All right, have a good day.